till 6.
Okay.
Steve, you're good to go.
Oh, okay. Peter, are you kicking us off?
Yes, welcome everyone to today's AESQ webinar. It's entitled What Makes a Good Process Capability Study. I'm Pete Tatey. I'm the team lead for the Process Control Methods Subject Matter Interest Group. And I'm very happy to introduce our lead speaker today. His name is Steve Hampton, who's a statistician from Precision Cast Parts Corporation, PCC. And so he and I are going to share the webinar together, but Steve's going to do the heavy lifting as we get into the core of the webinar. Let me start off with a little bit on who we are as a subject matter interest group, our community of practice, which is available on the LinkedIn site. And so just a little overview here on the webinar. We are recording today's webinar, so it will be available on the AESQ website. And the link is shown on another slide, as we will see. It'll provide you access to the presentation material as well as a video recording. We'll be taking questions using the chat feature in this WebEx webinar. And please, we ask you to remain on mute during the presentation. Again, that will help our presentation. Next slide, please. So why this webinar? Process capability is a very important part of process control. It helps us to assess whether or not a process is repeatable. Very important and capable of meeting the engineering requirements. And there's a lot involved with process capability. And today we want to kind of go through some of that and some basics of it and expectations that come out of AS 13100, but also the reference manual 13006. So we want to show the use of statistical tools, conducting a process capability analysis, and to promote the free documentation that we have. That's on the supplementary web page on the AESQ website, supplemental materials. Again, we'll show you the link for that in a second. And any questions you may have. So as far as the reference manual goes, RM 13006 has it's all about the process control methods. If you were in December's webinar, we gave an overview about what's in the manual. There's a very detailed section on process capability and the different indices, the methods of calculating them, and the application of those indices. But that's what leads us to today's webinar. The purpose of the reference manual, though, is to raise that overall capability for our suppliers, especially when it comes to process control, mitigation, identification, and mitigation actions through RM 13004, those producing PFMEAs, and the process control methods that support that mitigation through RM 13006. And as mentioned in prior webinars, RM 13006 supports the implementation of AS 9145. That's the advanced product quality planning and production part approval process. And process capability is a big part of that, especially for the variation management of key characteristics. The next slide, please. So the process control method subject matter interest group has the responsibility to manage the manual, update the manual, and provide webinars on key elements of the manual to help provide clarification of of the of the guidance that's contained in it, how to use that guidance to meet the requirements in chapter 9 of AS 13100. This subject matter interest group is made up of experts across the globe from many different companies that are members of the Aero Engine Supplier Quality Group. And so we are accountable to assure that this particular important aspect of AS 13100 is maintained properly and supported. So we're here to support the supply chain for AESQ. Next slide, please. So these are the members of the subject matter interest group that make up the process control methods. And again, from Pratt & Whitney, GKN, PCC, MTU, Honeywell, Rolls-Royce, General Electric, Safran, these are all the member companies. And again, these are the companies that provide members for each of the subject matter interest group teams. Next slide. Where can you get help? So after this webinar, you can go right on to the AESQ SAE website. You could pull down any of the free reference manuals. I call them the gold books, whether it be process control methods or defect prevention tools, human factors, FAI. There's a number of these different gold books available for free to the supply chain, to AESQ. Also, we would love to have you participate on our community of practice. Go to our LinkedIn site. Again, the URL is at the bottom of the slide, and ask questions, become part of our community of practice. And we will be happy to answer any questions that you may pose in that community. Next slide, please. So at this point now, what I'd like to do is turn it over to Steve, who's going to give us a walkthrough process capability in RM 13006. Thank you, Steve, and take it away.
Okay, perfect. Yeah, thank you, Pete. I'm glad to be here. Like you mentioned, my name is Steve Hampton. I'm with PCC Structurals. I've been there for 16 years, and I've been in the process control group for 7 years now. Process control and stats are my jam. It's my favorite thing to talk about. So I'm really excited to go through the humble process capability analysis and tied into the reference manual 13006. That is a great step for you to get in there and have some guidance as you do your own analysis. So this is just a snapshot of the key sections related to just process control. Since there's so much goodness in there, this would allow you to just focus on the process control aspects if that's what you're doing or interested in the manual with your analysis. So I'm not going to go through each one of those, but the highlight of what we'll be going is basically the importance of process capability, which Pete has touched on, the key principles of the process capability analysis. Go a little bit more into the indices, because I think people get wrapped around the axis with, PPK versus CPK and PP versus CP. So we'll dive into that a little bit more. Some guidance on non-normal data, though this will just try and whet your appetite, because we'll have a whole webinar just on non-normal data analysis. And then we'll do some live case studies that hopefully you can kind of see me go through some data, and hopefully I, maybe even mess up a little bit, and you can see what happens when you're in the trenches dealing with real data and working through your own problem. So I hope you can come away basically with all your capability analysis in the green box, and you would know why it's in the green box versus being in the red box on the right there. So why does process capability matter? I mean, the fundamental thing is your customer is most likely asking for it, for you to prove that you're capable. So that really bumps it up in the priority list. But there's a lot of value that you could get for your own process and process control. So I like to think of it as a way to give your process a voice, and it's from the viewpoint of the customer. So are you going to be able to satisfy your customer with the way you're performing right now? And you can actually even glean a little bit of information on, could you satisfy them if you take some reasonable actions? On the right there, you can see, turn on my laser pointer. You can see just what it looks like for the normal distribution as you reduce variation and your capability increases. So you start with this more wide distribution that, as the PPK of 1, you're basically fitting in plus or minus 3 standard deviations into your spec band. And then as you go all the way up to the holy grail of PPK of 2, your 6 sigma, so you can fit 6 standard deviations on either side of where your mean is. That really allows you to guarantee to your customer that you're going to be providing the parts they need to their specifications. And I really like that you can take a very complex process and oftentimes distill it down to one number. So that's a lot easier to talk about than trying to characterize it in a bunch of other numbers that might, like, a mean and a standard deviation, and somehow put that it compacts it all into a nice little package for you. So that's another thing I really like about the process capability analysis. And also I like that, not only tells what you're doing, but lets you know where you can get to. Like I said, we'll go into a little bit more of like what that means in the process indices. And it lets you know where to spend your resources. So, by having a single number for a process, you can do a Pareto on those and say what could be the most impactful and what should I go after. Or you can even split it up if you have KCCs that are labeled by critical, major, and minor. You can Pareto inside of those categories. And so you can, we don't have infinite resources at times. You make sure that you're applying it to the things that will make the most impact for your customers and your business. So to me, I think those are the key aspects of why the process capability analysis matters. So the aspects of a good process capability analysis, and really this is the aspect of anytime you're collecting data, is you have to trust your measurements. And so there's a whole reference manual, RM 13003, that helps you get through that, because I think the MSA is another thing that people don't give as much detail or thought about. Just like process capability, it's more like, oh, I've been asked for it, let me get through it, hope I pass, and then never get asked for it again would be awesome. But once again, if you do it right, you understand it, there's a lot of business value that comes from it versus just making a check the box kind of exercise. So the reason that you want to be able to trust your measurement system as you're taking these values that'll go into your capability analysis is because in this middle box here, if you have so much variation around the measurements you're taking that you can't tell parts apart, then you are not going to have the right level of resolution in the data that you're putting into your capability analysis. And also you might show that, oh, I'm actually, capable, but if you have so much variation that a measurement actually could be out of spec, even though you're measuring in spec, then the capability analysis is kind of lying. So you definitely got to make sure that before you do anything and go guns a-blazing, once you're all like jazzed up from this presentation, you got to make sure you can trust your measurements first. And I thought this was really cool because I love being able to tie, the statistics and the process control stuff we talk about to like real world events. So I found this as I was Googling on MSA stuff. And in 1928, there was a Swedish warship, the Vasa, that was supposed to be the greatest thing ever. And it sailed out to sea and immediately sank, which is, not what you really want for your brand new warship. And part of the reason is archaeologists have discovered by looking at rulers around the construction sites that the workmen were actually using two different measurement systems. One was using a Swedish feet, which had 12 inches, and the others were using an Amsterdam feet, which had 11 inches. So it made the ship asymmetrical because it was thicker on the port side than the standard side. So even back in the day, a measurement system analysis would have proven its value. So you could click on the link there if you wanted to dig into that a little bit more. But once you feel that you can actually trust your measurement system, it still doesn't mean you can trust your data, because we have an example down below that's a bunch of outliers, those red asterisks. So are those real, and you actually do need to include them, or are they somebody wrote down a measurement wrong? A sensor is on the fritz, so it's not collecting real data. Or they could be that that's a process violation you had, or a variance, and you put in a corrective action for it, so it's no longer actually part of your process. I fixed the machine, we put it in the PM, that data point is never happening again. So if it's not going to happen again, then really it's not your process, and it shouldn't be in your capability analysis. So every new engineer that I can influence, the first thing I tell them is, as much as it's awesome with our new statistical programs we have, the first thing you should always do is look at your data and make sure that it makes sense and you can trust it. Okay, so we have a measurement system we can trust, and we have data that we can trust, but now do we have enough of it? So we want to make sure that we can actually capture the process variation across our different shifts and our different machines. And we also need to make sure that we have enough data that the estimate that it puts out means something. So that's why I love anytime, really any analysis you do in statistics, if you can get a confidence interval with it, I highly suggest you use that, because it lets you know how well does that value actually, or how trustworthy is it. So if I had a PPK of 1.33 and I patted myself on the back and I'm about ready to ship that off to my customer and say, we're good to go, but then I turn on my confidence intervals and they're like 0.2 to 2, well, I have a number there, but it could be anything at that point. So that is not a useful PPK. So I need to actually go in and collect more data for that to be useful. So I highly recommend that you make sure you're looking at your 95% confidence intervals around values you're producing. The other thing, I've actually not seen this, but when I was being trained, it was one of the horror stories that the trainer talked to me about, is make sure that your data is in time order. Luckily, PPK doesn't care about that, but if you're interested in a good CPK value, if someone and how it happens is they didn't do a control chart, so that, because that will identify it immediately. And so they sorted the values because they were trying to see something, and then they forgot to unsort it, and then their capability analysis. And what it does, you can see here, I put a red line, the capability analysis on the top is what happens when you do it in time series. So we have a 1.313, and then when I sorted the same data, and then you can see here, we have the same PPK, 1.3, 1.3, but the CPK goes to 269, because the variation between each data point, because we sorted it, is almost nothing. So the within standard deviation goes super low. And good question, Darren. I believe so, but Becky can confirm for us about the presentation being available. And then, yeah, so you definitely need to make sure that it is in this order that it's being captured. And if you don't have enough data, there's a trick where you can create a part family. So similar parts can be put together so that you can increase the data. And so, you want to make sure that the customer agrees with what you identified as similar parts. But we do have in the reference manual 13,006 that we're talking about, section 9.2 goes over how to do that. And this is probably the most missed step. So if you are using Minitab, I suggest you use a capability 6-pack because it forces this like right in front of your face. And if you are using Jump, like my company is, and so that's why I have my charts are Jump charts, if they look a little different. Make sure you're using the control chart builder with the specs in the column so that you'll get both the control chart and your capability analysis, or the process screening platform. But you have to make sure your process is stable. And why? And this is actually will be another webinar, so we're going to dive into this super deep for you. But if you are out of control, then that means that your process capability analysis is only valid for the data you're collecting and not valid for any data going forward, because you don't know what the next value is going to be because you're not in control. So it, your customers want to know what your process capability is for things you will ship to them later on. So if you're not in control, then they're not going to really care about things they've already received as much. So, and then the other thing I want to just bring up from my process control experience is you're looking at the stability of your output. But the output is really driven by the stability of the processes that affect that output. So the next layer, if you really want to make sure that you are going to keep your values in control, and thus you can trust your process capability analysis, is you really should be looking at the KCCs for what the output. So like if this is a thickness measurement of a part in this left IMR, you should also dig down next level and look at the KCCs of that part and that thickness characteristic, and those should be in control as well. Because if those aren't in control, then it really is most likely that you're just getting lucky with the batch sizes or the batches that you picked, that your output is showing in control. So that's just my little advice: is dig that next layer deep to make sure that the KCCs that are driving your response that you're doing the process control on are capable. So this left IMR, it looks good. The I portion, the individual points, nothing's out of control. Don't see any trends. The dispersion chart down below, there's some points that are out of control. So it's possible that the control limits up here on the I portion might be a little wider than they really should be, because ideally all the points in your dispersion chart are in control as well. But even if you were to suck in those control limits on the upper I chart, you still really wouldn't pop anything out. So I would, give a thumbs up on the stability for that process. If we pop over to the next IMR, it still looks good. Worse, I mean, we have definitely more of the I portion points out of control, and more of the dispersion chart out of control. It's not horrible. I would say it's kind of, borderline. I wouldn't necessarily say like no go on doing a process capability analysis here. It is interesting that there's like this shift, or yeah, it's more of a shift of these points right here. Switch to my pin here, right here. You see how that kind of shifts up. I did put in the Westgate rules of number 3 and number 5. So 3 testing for trends, 5 testing for shifts. It didn't flag anything here, which I thought was interesting. But I would, if you don't turn those on normally, it's good if you see something like this, turn those on, see if it flags, and just interrogate that more, because that's definitely a little questionable. I'd be interested to dig into the KCCs around this and see what they say about it. But still, probably at this point, like say, yeah, we could put that into a process capability analysis. Now the X bar, I just showed the X bar portion here, but this X bar, this is red flag. Like, what happened? We obviously had a shift right here. Now, hopefully this was intentional and this new process is actually where you want to be. And if that's true, then you can just don't include that in your analysis. This is your new process going forward. Do your process capability on that, and that actually looks pretty good. If you do not know why this shifted, that was not intentional, so you have no clue if it's going to shift back, no process capability. So you need to understand that shift before you do your process capability analysis. And so, oh, and I apologize. I did answer one kind of question on the fly, but now that I'm kind of into it, I won't be able to answer questions from the chat. But it looks like Pete is answering for me. So just wanted to let you know I wasn't ignoring them, but I really can't see them with the way my screens are set up, and we'll circle back around. So last, I have this X bar S, and like you can see, like, well, basically we had a shift, which once again we want to understand. But oh, everything's out of control. So you're telling me I can't do a capability analysis because I don't know, everything's like not stable. The problem here is that there is a ton of parts in the subgroup, and what that does is it shrinks those control limits like unrealistically. So this is where, and this is like my favorite control chart, we go to a between, within, or a three-way control chart down here. So we get a third chart, and it basically transforms the top chart into an IMR. And then we also can keep our dispersion within dispersion chart of an S down below. So now you can see appropriate control limits, and assuming that this going forward here is the process that we want to have, that looks great. There is a little bit of a drift on our dispersion, so we're slowly increasing the within subgroup variation. So that might be something we'd want to dig into before we go gung-ho on a capability analysis. But it's once again kind of a borderline state. So three-way or between, within chart, depending on what program you're using, is definitely a very valuable control chart that I haven't seen a lot of use of. So I threw out the words. Well, I think I threw out the words. And when I practiced, I threw out the words. Each one of these is being a batch or a subgroup. So what is a subgroup? Also known as a rational subgroup. So it is a representative grouping of parts that are processed close enough together in any time and or processing conditions that they have a very low likelihood of a special cause variation occurring within that group. So it's really nice to use because it allows to sample from extremely large groups. So I can just grab a bunch of random parts from a huge batch, put it into a subgroup, and it represents the overall population of that batch. And so I don't have to measure everything. It also gives a much better within or short-term variation estimate versus trying to use like a moving range in the IMR control chart. And then also it get that better short-term variation analysis helps with a better CP and CPK in the capability study. So some examples are batches of parts between a machine setup. So I set up the machine, ran a bunch of parts, and then stopped. So that can be considered a subgroup. Or I use a different die. So I had die A, I ran a bunch of parts, so that's going to be subgroup 1. Then I put die B, ran a bunch of parts, it's going to be subgroup 2. Parts that are made over a shift or a day, parts that are made on different machines, parts that are made on different raw batches. This is an interesting one. I actually have a lot of kind of thoughts on it, but we're going to discuss this actually in our subject matter expert group. Multiple hits on a similar surface of a large part. So especially with structured light becoming more and more popular, it's a lot of data we get from surfaces. So you can consider that a subgroup and put that in as your subgroup. But you need to talk with your customer about that because it actually kind of changes the definition of what some of the outputs of the capability analysis means. And you got to make sure that they agree with that, understand that before you go full bore. So that one's got a caveat. We're going to be working on trying to put some guidance around that. And so hopefully we'll have that into a future revision of the reference manual. So that will be exciting. So the other key thing is to make sure that you know what distribution you use. The math is all based upon the values, the point estimates of the shape of the curve, and it's not your actual raw data. And so you have to make sure that curve fits your raw data in a way that it represents it well, and so that what gets outputted from the math behind the capability analysis is correct. And so here's an example of if you just tried to fit a normal distribution to something that had a natural bound at 0, such as a thickness measurement. In this case, we got lucky. The normal distribution actually fits okay on the right-hand side of the tail. It kind of, it actually is being a little optimistic, because we have the green bars from the histogram are above the fit of the tail. So if you looked at your expected versus your actual of the fit of the capability analysis, you're probably going to see that they don't line up as well as you'd want to. But it's, yeah, just really important that, you know, you don't just run an analysis, let's put it on, just use normal for everything, and then report out your PPKs, because most likely you will get burned by non-normal data, because it is out there. And then you need to know what indices to use. You know, I am a big fan of PPK, just as your like kind of go-to, because it communicates just what you're producing, and you don't have to worry about subgrouping and so it's a pretty robust and from how you set it up, or yeah, how the data's set up and what you get out, and then it just says this is exactly what's going to go on with my process. And then you also need to understand the possible long-term shifts. So this kind of falls into when we talked about getting enough data, not only from your confidence interval standpoint, but you got to make sure that you're taking them a long enough period.
Steve, your sound seems to have dropped.
Capability analysis right here. If you did that, then you're not accounting for a piece of equipment, and so your capability analysis is has some blinders on. Or what if you have like a seasonal effect? So you can see we have the artificial seasonal effect that I grabbed, and what if you ran your process capability here? If you did that, you're not taking into account like what actually your process is putting out. So, and the control chart probably will look pretty well on this as well. So you need to sit back and think about the data that you grabbed, and does it grab the process variation that you have across time and equipment and shifts and stuff like that. So, okay, I wanted to dig into the process capability indices a little bit, and I want to do it in a little bit of a different way, because I think the biggest thing I see is confusion between CPK and PPK. So real quick, I'm just going to go over here, and just the CP and PP will tell you how well your process variation fits into your tolerance band. CPK and PPK tells you how well your process variation combined with your process bias fits in your toleration band. So you're really only looking at the variation of your process in CP and PP, but then you also look at the location of your process when you add in CPK and PPK. So that's why CP and PP will be better than their corresponding CPK and PPK, unless you're perfectly centered already. And then CP and CPK will use the within, or your short-term standard deviation, versus PP and PPK will use your overall standard deviation. And that's why you'll generally see that PP and PPK will be larger than CP and CPK. So what I tried to do here is I have 20 batches of material, and I made some fake data where each subgroup has a mean of 0 and the standard deviation of 1. So they're just little normal standard distributions. And I think there's like 30 parts in them in each one. And then each one I randomly assigned an integer offset between 1 and 5 to get kind of this variation. And so CPK and CP looks at your data in this way. It says, okay, I'm going to care about this subgrouping, whereas PPK and PP looks at your data like this, and it just says, I just rolled up every piece of part data you have, and I'm going to look at it's one big distribution, and I'm going to do calculations off of that. And so when we look at the difference, so this is the original chart we had here, you can see the difference. And here's the capability analysis from that. So we can see our CPK is 0.698. And because we have a spec of -2 to 6, so our target is 2, which is, right here. So, and here's our spec limits. Should have put them in now that I think about it. And our PPK is 0.44, and our CP. So we could center and remove variation between the subgroups and center it, the process. Then we can get to 1.27. So it's actually, we could get there. I mean, if we did put some elbow grease into this process, we could get there. But right now we're really struggling. So let's say I can actually just make all the subgroups have the same mean. So I'm going to just center all the subgroups on the current mean of 3.8. And so what you can see is that our CPK did not change. So from this, I'm going to say 0.7, you can see here, it's still 0.7. Because once again, it is taking the average of all the subgroups, but it really doesn't care where they're located with respect to each other, because it's basically doing this in the background. It's lining them all up and then saying, okay, what's your standard deviation now? So that one doesn't change, but you can see that now PPK went from a 0.44. It now matches the CPK as 0.7. So we have 0.7, 0.7, 0.7. So by getting rid of all the differences between my subgroups means, I have now made my PPK equal my CPK. And then if I wanted to get even better, I would have to now shift the whole process down to 2. And if I did that, my PPK will become my PP of 1.33. And since everything's lined up and there's no difference between PPK and CPK, because my within standard deviation equals my overall standard deviation at this point, you can see that my CP is the same. So when you start with PPK, which is just looking at everything as one big distribution, you can either reduce the differences between the subgroup means, and then that will drive you to CPK, and then you can get to, by shifting the mean of the process at that point, get to CP. Or your alternative route is you can say, I'm going to go from PP, I'm going to shift the entire, or PPK, I'm going to shift the entire process down. So I would take this whole process up here and shift it down to, so that blue bar, which is the current mean, would shift it down here. We'd still have all the variation between the subgroups, but I would increase my PPK now to match my PP of 0.8. And at that point, I would need, if I could get rid of the variation between the subgroups, I would then be able to achieve a CP. So you have two alternative paths to go from a PPK of what you're currently producing to CP, which is really the best you can do without getting into common cause variation, which is a science project and is going to involve most likely a lot of brainstorming, process walking, fishbone diagrams, and DOEs. There is a little bit of a caveat on the IMR. I started with the X bar S there because it's the subgrouping it's much clearer that way. But really, the difference that drives CPK and PPK on an IMR style data set is just shifts. So because it's the moving range is looking between each consecutive point and and that's where the within standard deviation. So here you can see that CPK is 0.39, PPK is 0.45. And we'll talk about that below because CPK really should never be less capable than overall. But if I artificially added in from that data these kind of shifts, and then I kind of made some of the data get a little bit closer to each other. So overall, the moving range is controlled by these groups of the points being very close together. You can see now that the CPK has increased, and it's much better than the PPK. So we had the PPK and the CPK more aligned when there was less of these kind of groupings that are shifting around. So the note on the IMR data is that if your CPK is lower than PPK and you're being asked to report CPK, I suggest you report both because really CPK should never be worse than PPK. And it only happens in instances where the moving range estimate of the within standard deviation just overstates the variation, and thus the CPK is lower. So a note on that guy. So to kind of summarize, PPK is use the overall variation as the current capability of our process. And we can then move to either PP or CPK by doing some improvement activities, if you're shifting the overall process or removing subgroup variation. And then that allows us to finally get to CP by solving whatever we didn't solve in going to CPK, which is solving the within subgroup mean variation or between subgroup mean variation. Sorry about that. Or PP, we have just shifted the process. So now we need to solve that between subgroup variation to get to CP. If you want to get better than CP, like, let's say your CP is 1.0 and your customer says, I need you to be at 1.33. Well, then now we start the science project, which could be a lot of fun because DOEs are awesome. But you got to get into your common cause variation at that point. So some guidance for non-normal data. It actually happens a lot more than you think. And so you check your fit to make sure you are actually having non-normal data. Be aware that if you're doing something like an Anderson-Darling test, if you have too much data, it will, any slight little deviation from normality, it's going to flag on. So if you have a ton of data, I'm a big fan. I've been taught, the fat finger or the fat pencil test, where you have your quantile plot, and you just kind of like put your imaginary pencil over it, and the pencil basically will lay over your points in the quantile plot. So if I were to lay a pencil, oh man, evidently a broken pencil over the data, and it covers it up, then you're good. Even though if you have so much data, those confidence intervals, those dotted lines become so tight that unless every point is like a perfect line, it'll flag. So you can't just trust if you're just pulling up a table of p-values from a normality test. And then you need to check your process too, because you might be like, holy smokes, I have non-normal data, but it might be just because you have a blended process, or it might be back to visualizing your data. It might be a bad data entry or sensor issue that you can actually take care of. And once you do, it's a normal distribution. If it truly is a non-normal distribution, then you really want to make sure that you fit the right non-normal distribution to it. So, look at Weibull and log normal are very common ones to use. You will not get a CPK if you're using a non-normal distribution. So just be aware of that. Don't try and dig into a bunch of submenus to try and see what box you need to click, because it's just not available. We put down as the last resort you can transform with Box, Cox, or Johnson, but it really muddies the water. and it makes it like hard to kind of interpret the outputs because things, it's a transform process. So the units are different and the shape is now kind of normal, but it's not the actual real data shape. So we put it as a last resort. Usually between finding a non-normal data distribution and figuring out why you might have non-normal, especially if it's bimodal, you can work your way out of having to use that last resort option. Okay, so I wanted to do some live, I know, very daring, some live demonstrations of some process capabilities. So let's do a standard analysis. And I put, is there such a thing? Because there's always all kinds of little details you have to deal with. So that's why for the standard analysis picture, it is a bimodal distribution, because that doesn't seem like a standard analysis, but it actually could be. So the first thing I want to say is that look at your data. So if we look at our data here, holy smokes, what the heck's going on here? Well, it turns out that that was a data entry error. So I'm going to go in, and yep, they forgot a 0. So I'm going to just correct that real quick. Good. There we go. That looks better, but we still have this weird bimodalness going on. So, a little bit of a flag there. So let's look at from a distribution standpoint. Okay. Well, obviously, this is not normal. And, so you have some options here. What's nice is, I have the ability here to fit this. This will actually fit some bimodal data. So I could, go to town now with this bimodal data because I have a good fit. But if you were to do your next step of looking at the control chart, well, okay, cool. It's in control. Well, you should know that the spec limits are basically here. Let's see, like here at 0.06 and negative 0.06. So since the control limits are so much wider than your spec limits, it's obviously a red flag. And what's going on, if I, I'm like, I'm going to put my process hat on, dig into this a little bit more, I'm going to drag this over. Holy smokes. It's because I have such different outputs from my line 2 versus my line 7. So I actually now split up the data and look at it. I actually have 2 normal distribution capability analysis I could do. And I have a very nice process improvement project I can take on to see why my 2 lines are not behaving like they should be. So now I can look here and say, okay, this line has a PPK of 1.09, and I have 0.854. So this is going to be the one I should probably focus on because it's driving more out of spec. I did look down here. I mean, this still, I would say, has a little bit of a fit problem. We probably have some outliers going that it's not perfectly happy, because I'm expecting the percentage from the upper spec limit to be around 0.5%, and I'm observing 2.7. So that's enough of a difference that I would flag it to kind of dig into the fit a little bit more. This one here, yeah, maybe not quite as much, but that one too, probably dig into it a little bit more. Probably driven by some outliers. And yeah, probably, actually you can see them right there. So yeah, so control chart flagged it for us. Awesome, thanks control chart. And then I can see that if the easiest thing is just try and shift the means, I could shift this mean and get it down to a PPK of 1.6 if I shifted the means. And I can actually get this one to a 2.186 if I shifted the means. If I needed to get even better than that for some reason, what's really cool from the control chart is I can actually say, like, oh man, look here, man, this section is really good. Like, why are we having such less variability? So I have even baked into my data already that if I can figure out why, I shifted from having a lot of variation to none, that I could actually even go to a PPK of 2.29, or if I shifted everything as well, a PPK of 3.5. So by using both tools, the control chart and the process capability, I have a lot of options on where I could put my resources and what I could get out of it. So that's a standard analysis. The next thing is, let's just look at a case of a between within. So once again, we're going to look at our data. And so you can see we have a lot of parts in each subgroup. So it makes it a little bit hard to see. So I'm actually going to change this to the box plots. And it turns out that this one here, we did some digging, and this one actually is a machine that broke. And so we put a PM, so that will not happen again. So that's not representative actually what my process is doing. So I'm going to remove that. Just hit and exclude it. Okay, so now I feel comfortable to be able to do my analysis. And so I'm going to now look at my distribution. So, it failed the Anderson-Darling here, but we have a lot of data. You can see those control limits, or not control limits, the confidence intervals are really tight. But my little fat finger pencil test, that looks good to me. I mean, visually looking at the data, yep, that looks good to me. So I feel confident in going forward at this point. So oh, I did not, oh, here we go. Sorry, skipped over this one. But once again, oh man, I can't go forward. I am way out of control. So, but my problem is I have 22 in my subgroup. So that just really shrinks down these control limits. So what I want to actually do is put it into my three-way, and hey, this actually looks great. But since I'm using a three-way control chart to say that I'm stable, I need to make sure I use a three-way control chart for my my capability analysis. And so you can see here just the difference. Using the standard way, it really overstates my within capability because it's only looking at one source of what we'll call within standard deviation, versus the between within is taking into the two sources of variation, and you can see that actually adds up to a much higher standard deviation that we'll use for our CPK. So CPK of actually 1.0 versus 1.5. So that is a quick look at a between within. And finally, as structured light, I don't need to actually close this, structured light and CMMs, very and complex parts end up with a lot of codes. There is ways. So in Minitab, I actually have an old slide here. In Minitab, you can do, if you go to Stat, Quality Tools, Capability Analysis, and you can go to multiple variables. You can do this same type of approach where you can have a ton of different characteristics defining a part, and put them into one analysis instead of doing it one by one. And this isn't in the slides I had, so I'll add this to the slides before we publish. And then in the JMP platform that I'm showing here, it's got a nice little process capability roll up. So I've assigned specs to each column, and it puts out a visualization of each one. So I can go through those if I want to, like, ooh, man, just real quickly scrolling, I can see that, there's there, this characteristic 6, we have some work to do. And So this is nice. I can visualize it here. But then I can also go down to, I have my capability summary that will show just a summary of PPK and PPL, PPU, PP, and I get my expected versus observed. So this is a nice way to see the fit, and it puts out this table, which is cool too. And you can go through and hover over and say, oh hey, and, what does this guy look like? There's the control, and it's in control. That's good. And if I wanted to dig in a little more details, like that's good. Now, I just showed this because this output kind of most aligns with mini tabs, where it's just putting out capabilities. Still, we've missed a important step. So I hope you're like screaming at your desk at me because you're like, you didn't check capability, you didn't check your control chart. So yeah, you would have to go in and make sure that you have all your processes in control. So good job screaming at me about that. But what I like a way to show these large scale is if I just making a data table out this. And like I said, you can put this same kind of output in Minitab. It goes directly to this table versus the summary one I had. But and then I'm just going to make a distribution of my PPKs. And so this is a really nice way to kind of communicate for a lot of capability analysis, just how the part overall is showing up is just to show a distribution of your the distribution of your PPKs. And I'm going to actually just change this to a little bit different. And I can see here that 40% of my parts are basically, or codes, inspection items are above 1.33. And I'm around a little less than 50% are above 1. So actually we have a lot of work to do on this part, but it's a nice way to convey where you're at, and with a very complex part with a lot of inspection items in a single chart. So, okay, so that's it for the live portion. Get these out of the way. So, oops. So in summary, have quality data you can trust, have enough data that you have appropriate narrow confidence intervals and capture the correct process variation. Make sure you use the correct distribution. Make sure your process is stable, and make sure you're using the appropriate indices to evaluate your process, which I'm going to just throw a plug out for PPK should be the starting point. And then finally, track and improve. And with that, I'll turn it back over to Pete.
All right, thank you, Steve. Excellent presentation. We're going to wrap it up now, folks. So we have more webinars on the way. There is a schedule posted on the AESQ, and it's also shown here in this matrix. The next one coming up will be February 8th, and Grant Braun on our team will from PCC also will be talking about process capability studies specifically for true positions in handling MMC. That should be very interesting discussion. So look for these in the upcoming events page on the AESQ website. Next slide. Yeah, there we go. Okay, so Q&A. Steve, we had one question that came up about subgroup sizes, and I want to ask the question exactly the way it was worded. Let's see, here it is. Here it comes, right there. So does a subgroup size of 3 mean you sample 3 units from a run? Or does it mean you measure the first 3 units, then skip the next 3, and then measure the following 3 units? That comes from Jeff.
Okay, yeah. So in general, the way that I approach subgroups is that should be a representative sample of whatever you decided the subgroup is. So, so like if you have a batch of 6 parts and you randomly select 3 out of it, or maybe it makes sense in your process to take the first 3 because that is representing something that's more important to actually capture a control chart. That could be fine, but in general, the way that when you learn about them is it's supposed to be a random sample that is representing a larger population for the subgroup. Um, and so, and it might be actually that you only produce 3. So I produce 3 off the die, and that's going to be my subgroup, and it's not necessarily random sample. It's just everything I have in there. There's some nice things in the control charts when you use subgroups versus like individual points, because you get to take advantage of the central little limits uh, the central limit theorem. So things will turn out, you might not have to worry about non-normal data when you're using subgroups. But yeah, that's generally the way that I've seen it, is that the 3 would be some random picking of a larger batch of parts. That doesn't have to be.
Mhm. Excellent, Steve. Abdul has a good question here that comes up quite a bit, where folks may not want to target the center because of wear on an expensive, let's say, die, and they might target it in such a way to allow for that wear to happen to maximize the life and minimize the cost of repairing. So he writes, I do not like centering my process in some cases because if it is being centered, there is more chance that it can go under where it creates bigger cost to repair it. I'd like staying close to the USL. When it goes over, it would cost less to repair. How does this situation be justified from a statistical perspective?
Yeah, I mean, that's perfectly fine. I mean, the statistics are just looking at your tolerance and assuming that like that's all that matters. And so that's a great point of taking subject matter expertise to know that it actually is better for the process and the customer, that I'm going to skew it to the top because there's less chance of rework, and I can actually produce parts longer by living there. I mean, you might say with a customer approval, you might say, hey, the upper tolerance is not as critical. So can we actually apply a little bit of a buffer to that and report our PPK versus that? We've had some instances of something like that. We didn't really get into it, but there's also the CPM care that
Mhm.
is an option, because that's versus a target versus just a standard spec band. So that might be something you'd want to look into as well, to be able to use
Mhm.
to show that you're actually achieving living in a different area than the optimal being centered in the spec bands.
And we do have one of the control methods in the reference manual called out with an example is called run charts with non-statistical limits when you're looking at specifically a warning limit and you're monitoring something like wear. And so you might want to check that one out as well. Another question here from Bob. What do you do when the process does not follow a parametric distribution? Your cyclical seasonal data, for example. Does anyone use non-parametric methods for capability analysis?
That is a good question. I have not had to deal with that. So seasonality is not anything from the data output we have. But yeah, there are definitely non-parametric methods you can use for capability analysis. I mean, even if you have, the hard part is really from the capability analysis doesn't care about the seasonality, because it's either you're capable or you're not. Now your control chart could absolutely show a disaster. Um, so you might have to do something like use a time series kind of modification, where you would adjust where your data is at versus like an Armina, like a Armina model, so that you're kind of gauging is your process where it's supposed to be versus where you are in the season. And so that could be a way to have your control charts be useful, even with large seasonality effects.
Again, looks like the last question I'm seeing was the software you were showing or illustrating. We saw a mini tab. Was another one SAS JMP?
Yeah. So yeah, we've used both, and
Okay.
they're both really good programs. And but yeah, we are now using SAS JMP as our statistical package, and that's what I showed the demo in.
So I think that uh, was the last question that we had. If there are more, you can always reach out to us on the Community of Practice site. Um, and I think that is really it. I think we can close up shop for this particular webinar. I want to thank everyone for participating. And thank you, Steve, for the heavy lifting you did. Becky for coordinating as always. So thank you all, and look forward to the next one, February 8th. Process capability for true positional features.
Yeah, thank you very much, everyone. Have a great day.